Hello everyone, welcome to our TESOL Global YouTube channel. This is our FPGA video series where we will explain different aspects of FPGA. We will provide different examples and demonstrate some projects. In this video, we'll continue explaining basics of Verilog coding with an example Verilog code. This is the third part of this video and we'll have another part, then we'll end this Verilog basics part. We also received a lot of requests for VHDL examples and basics. So we'll work on that after the fourth video of this Verilog Basics series. So now start with the common logic values being used in modeling hardware are logic 0 or false, logic 1 or true, X or unknown. It is also known as don't care. And last part is Z or high impedance. So the last two values X and Z, they're mainly used for simulation purposes. So in simulation, all unconnected nets, they are set to Z and all register values set to X. Now here we have an example of AND gate with unknown and high impedance inputs. So if we have the normal logic inputs like 0 and 0, then we know the AND gate output will be 0. And if it's 0 and 1, then it will be 0. If it's 1 and 1, then it will be 1. But if we have a 1 and there is an unknown, then the output will be unknown. Similarly, if we have a 0 and X, then the output will be 0 for AND gate, because in AND gates, if one input is 0, then it's all other, like the output will be always 0. And next, if we have 1 in one of the input and Z high impedance in one of the input, then our output will be unknown. And if we have high impedance in one input and unknown in another input, then the output will be unknown as well. So other primitive logic gates will also act similarly. If there is unknown or Z values there, so it will act similarly to this AND gate. So now we'll look at the primitive logic gates in Verilog. The built-in logic gates, also known as primitive logic gates for Verilog cores, and those are AND, NAND, OR, NOR, XOR, XNOR, NOT, and buffer. So here you can see the symbol of the primitive gates. So we also can see the instantiation for this gate. For AND gate, it will be output and input 1, input 2, or it can be more inputs, but there will be only one output. Similarly, for AND, it is output in 1 and in 2, or like there can be other inputs as well. For NOT gate, it will be out and in, and for buffer as well, it will be out and in. There are also primitive tri-state gates where the output is tri-state control. These are buff if 1, buff if 0, not if 1, not if 0. So, for example, if we look at buff in 1, then if the control signal is 1, then the input signals will go to output. So is instantiation is also like you can have the output, then the input and control. Then if we look at a NOT gate, then for not if 0, we can have the input and output, and when the control is 0, then the input will go to the output. So in summary, the tri-state gates commonly have input output and a control signal. Control signal is mainly used to maintain the output coming from the input. In primitive gates, some important points are the output port must be connected to a net or wire. Input ports can be either nets or register. These are generally single output with any number of inputs theoretically. We can use an optional delay for simulation purpose only. This delay is ignored by the synthesizer when we try to build the practical circuit. Now in the next few parts, we'll mainly discuss different important operators for Verilog. So first here you can see the arithmetic operators. So arithmetic operators can be plus, minus, multiplication, or division. Then we have the relational operators. So the relational operators can be greater than, less than, greater than equal to, or less than equal to. We also can have shift operators. So shift operators mainly represent logical shifts, for example logical left shift or logical right shift, or arithmetic left shift or arithmetic right shift. Moving on, we have some other operators like bitwise operator. So bitwise operators can be AND, or XOR, or like NOT gate. So we can also have logical operators like and, or, and there is a not as well. So we have an example here to show the difference between bitwise operators and the logical operators. So here we have a character A which represents 40, and we have a character B which represents 30. So character C is the output. So in the case of the logical operator, if we do A and then B, then the output will be 1. So here both the 40 and 30 are greater than 0. So that's why we're getting 1. So if we had, for example, A is 40 and B is 0, then we will have C is equal to 0. Now in case of bitwise operators, so if we do C is equal to A and B, then it will do AND operation bit by bit. You can see here for 40, you can see the binary number, and also for 30 you can see the binary number. So if we do A and B, then we'll have 0 0 0, then 0 1, again 0 0 1, 0 1 1, we'll get 1. Then whenever we have 0 in any of the input, the output will be 0. So you can see the bitwise operation output at C. Now moving on, we can also have equality operators like A is equal to B, or not equal to B. Also A is equal to B, and A is not equal to B. If we have two equals, then it tests logical equality. So it tests for 1 and 0, and all other will result in undefined. Then if we have three equals, then it tests 4 state logical equality. It tests for 1, 0, high impedance, and unknown. Now moving on to the conditional operator. It mainly have three operands. So the output will look for a condition, and there will be two expressions. One is expression 1 and expression 2. So again, we can say for the output, it will mainly look for a conditional expression. Then the first expression will be a true expression, and the second expression will be false expression. Next, we are looking at reduction operator. So in reduction operator, it can also be AND, or XOR. and not similarly. So the reduction operators mainly give one bit output by performing the bitwise operation over a single vector operand. And reduction operator work bit by bit from right to left. So here we have one example. So we have I1, which is 4-bit hexa number 6. So we want to do at the output reduction and I1, reduction or I1, and reduction XOR I1. So here the reduction will be like this. For AND I1, it will do first 0 and 1, which will be 0, then 0 1, which will be again 0, and then 0 0, which will be 0. So it is doing bit by bit operation from right to left. Now for OR operation, it will be 0 and 1 1, and 1 1, which is again 1, then 1 0, which is 1. So we are doing the OR operation from right to left, and it's mainly reducing the number, and it's giving us only 1 bit output. Now moving into some other Verilog operators like concatenation. So in concatenation, it takes different number of operators and concatenate those. Here we also have one example. So we have I1 is equal to 2-bit hexa number 2, I is equal to 2-bit hexa number 3, and we have I3 is equal to 4-bit hexa number 8. So you want to concatenate in this way. For example, we are looking at the concatenation of I3, I2, I1, or we are looking at the concatenation of I3, I2, and 2-bit binary of 1, 1. So the output will be like this. So you know for I1, the binary of the hexa 2 will be 1, 0. For 3, it will be 1 1, and for hexa 8 the binary will be 1 3 zeros. So if we look at the concatenation, the first concatenation output, which is I3 I2 I1, then first we'll have the hexa 8, then we'll have hexa 3, and then we'll have hexa 2. So if we convert them to the binary, so it will be 1 3 zeros, then 1 1, then 1 0. Similarly, if you look at the second output, which is asking for the concatenation of I3, I2, and 2 binary of 1, 1. So it will be again for the hexa number 8, the binary is 1, 3 zeros, and then we have I2. So for I2, the binary number for hexa 3 is 1, 1, and we have the 2-bit binary of 1, 1. So for the second output, you can also see the concatenation of I3, I2, and 2-bit binary of 1, 1. So now we'll look at the replication operator. In replication operator is mainly replicate an operator as per the number of times of replication declared in the code. So now we'll again look at one of the example. So here we have in the input 2-bit hexa of number 2 and 2-bit hexa of 3. So we want to look at the replication of these numbers at the output. So first one is we want to look 4-time replication of I1. So you can see here at the output it will be 1 0 1 0 1 0 1 0. So 1 0 is replicating 4 times, and then we have 3 replication of I2 and 2 replication of I1. So here you can see the 3 replications. So for hexa 3, the binary number will be 1 1. So we can see here the 1 1 3 times, and the I1, which is 10, is 2 times. So now we'll look at 4-bit counter as an example. So this includes multiple things we discussed in our previous lecture and today's lecture. So here you can see first we declared the module, then input output. Then we have declared the clock signal as wire. So from our previous lecture, so wire is here a net type interconnection, and then we have output as register type variable, and we declared the output as 3-bit. Then we have the parameter, which is div value, and here we have different option to select. Here we are selecting 10. This is mainly we are selecting for the simulation. We'll discuss it during the Modelsim simulation demonstration. Then we have another integer type variable, which is we declared here as 0. So the clock count is the integer type variable. Then we also have the equality operator in this code, which we discussed today. Then we have a logical operator, so it's logical OR. Then we have arithmetic operator, so here we are doing addition. We again have the logical operator. So here in the Verilog code, we are using the clock divider counter, which we used in our last video. And this counter is mainly helping to do the counting. So we are using this clock divider so that we can see the LEDs are counting in the Max10 development board. If we don't use this kind of divider, then and if we run the code for example in 50 megahertz, we will not even able to see what's happening in the output LEDs. That's why we are using this divider, so that the clock will be slowed down and we can see the counting is going on. So here in the 4-bit counter is very simple. We have a reset, so if you press the reset, then the output will become 0, and otherwise with the clock division, when it will reach to our expected clock division value, then the output will increase by 1. So next we will look at the Modelsim simulation. Before going ahead, we would like to ask you to subscribe the channel if you are benefited from our content. Also click the ring bell to get notification whenever our new video will be released. Stats show more than 50% of our viewers didn't subscribe to our channel. So please subscribe and help us to grow our channel so that we can provide much more quality contents. So now looking at the Modelsim, so we already have written the code for the Modelsim, and I also wrote the test bench for this 4-bit counter example. If you want to know how to configure the Modelsim and how to install it, you can find the link of our previous videos where we explained how you can configure the Modelsim for simulation, and also you can also check how you can install Modelsim in your computer or laptop. So coming back to the code, here we are looking at the 4-bit counter. So in the input, we have clock and reset, and we have output. So we declared the clock as wire, and we declared the output as 3-bit register. So we are here using the clock divider, which we used in our previous video. So in this case, we are using the division value as 10. We also have the division value of 25 mega and 50 mega to be used in the Max10 development kit. So we'll mainly use the onboard oscillator in Max10 development kit, and we'll use it to convert it to 1 second or something like that. So but if we try to use it these numbers in the Modelsim, the simulation will take longer. So just to make the simulation shorter, we are using number 10 as the division value. Then this part of the code we already have discussed in our previous video. So this number is mainly being used to divide the clock, and this part is mainly the counter example. So here if we have reset, then the output will become 0, and if the reset is not working, then the counter will keep counting. Here you can also see when we will have the reset, this value will also become 0, so that the clock division number will start from 0. So now moving into the test bench. So here you can still see we have selected the time scale as 1 nanosecond. It means every action will happen after 1 nanosecond. So then we just declared the input and output, and here you can see we're asking the simulator to change the state of the clock after every 1 nanosecond, and the reset will appear, or the reset will change its states after 20 nanosecond, 200 nanosecond, and 250 nanosecond. So after 20 nanosecond, the reset will become 1. So if when it's 1, it means it will ask the counter to keep continuing the counting, and when the 200 nanosecond will appear, so the reset will become 0. So when it will become 0, the counter value will also become 0, and it will keep 0 until 250 nanosecond, and after 250 nanosecond the reset is again becoming 1, so which means the counter will start counting and continue counting again. So now if we look at the simulation, so first we have to add these parameters into the waveform, and then now if we run the simulation, I'm just running it for some time, and now let me feed this waveform into the window. Here you can see, or let me zoom it a bit. So yes, here now you can see first the reset is 0 from here to here, and the output is 0, you can see here. Then when the reset became 1, the output it starts counting with the clock, and it continues counting. Then when again the reset becomes 0, it make the variable of the clock count 0, and also it also make the count value 0. So this 0 will continue until the reset will again become 1. So when the reset become 1 again, the counting is again continuing. So you can see the counting value is going on. So whenever it's become 4, like 1111, then it will again start from 0. So we selected the output as 4-bit output. So whenever all the 4 bits are 1, it again starts from 0 counting. So next we will move to Quartus Prime. So in Quartus Prime we'll synthesize the code, and we'll upload the code into Max10 Development Kit, and we'll see the output of this Verilog code in the LED. So now if we look at the Quartus Prime, so again we have already written the code in the Quartus Prime, and we configured the Quartus Prime for Max10 Development Kit. So the code is showed for the Modelsim, and the code here is a bit different. If you remember in our Verilog Basics first video, we discussed that the LEDs, or the onboard LEDs in the Max10 Development Kit, these LEDs, they are connected in active low. So it's mainly if you have 1, it will show 0, and if you have logic 0, then it will show 1. So to just compensate that, in that video we use an inverter at the output so that we can get the correct output. So we'll do the same thing here as well. So if you look at the code, you can see here is this, as I mentioned, a similar code, just this part is different. We added one inverter at the output so that we can get the correct output value or the correct count values. So if you don't connect the inverter, it's still correct, but it will be difficult to understand. So that's why we just use the inverter. Now we'll compile the code. As we mentioned before, it takes a bit time to compile it. So the code is now compiling. So it's now compiled. So one thing I forgot to mention here, you can again see we used the 50 mega. So, but in the Modelsim we used 10 mega. We used 10. So the reason we are using 50 mega here is we'll use the 50 megahertz onboard oscillator. So when it will convert, or when the clock divider will work, so it will generate 1 second delay. So we'll have each count after 1 second. Now let me show you the pin assignments. If you go to the pin planner, here you can see I already configured the pins. So this output, these 4 outputs are the onboard LEDs, this ones, and we selected the onboard push button switch, this switch, as the reset button, which is this one, and the clock pin is connected to pin M9, which is default pin for 50 megahertz clock or 50 megahertz oscillator. So another thing I would like to show you is the netlist view or the RTL view. So if we go to the RTL viewer, you can see the RTL structure. So here you can see this, up to this part is counter, then this is the inverter here. So this is causing the inversion of the numbers, so that we, as I mentioned, we can see the values in a way that which is easily understandable to us. So now we'll upload the code to Max10 Development Kit. So you can also see the Max10 Development Kit in the sub window. So if we now double click the programmer, now we have this. We already configured this with the FPGA we have in Max10 Development Kit. If you don't see it, you just have to click the auto detect, then it will automatically detect the FPGA you have in your kit. So now if we just load the program, if we go to the output files and we'll load the .sof file, then I'll click programmer configure and then I'll click start. So you can see it's now 100% successful, and here you can see the LEDs are doing the counting. So this counting is going on in every second because we configured the divider as 50 mega and we selected the oscillator here as 50 megahertz. So now this is the reset button. If we click this button, you can see it became 0 again. If we leave the button, It will start the counting again. So it will count from 0 to 15. It's mainly 4-bit counter, so it will have 16 states from 0 to 15. So again, if we just click it, it just reset the counting. Then again, it's starting the counting. So this is the end of the demonstration. So this is the end of the video. You can download these Verilog codes from our TESOL Global website. The link is given in the description. In our next video, we'll continue looking at the basics of Verilog coding. And the next video will be last part of the basic of Verilog coding. And then we'll move to the basics of VHDL coding. We received multiple requests to make some videos on VHDL. Please subscribe to our channel for more videos like this. Would like to thank those who already subscribed and helping us to grow our channel. Add likes and comments and give us suggestion for like what kind of video you want us to make. Follow us on LinkedIn, Facebook and Twitter. Thank you for watching. See you next time.